Thank you. Thank you very much for the introduction, for the invitation to come to this research day and the opportunity to tell you a little bit about what we've been doing in the area of materials design from our chemical modeling background. So today I will mostly discuss materials design for sustainable technologies, and so we looked at different. So here is a list of different projects going on in the team, and so on the electronics front, we are looking at super hot semiconductor materials. So that's what I will be discussing in detail today. But we also look at the resistance to oxidation, or the stability in air of emerging nanomaterials and semiconductors. We also look at alloy catalysts for important alternative to industrial processes, such as the nitrogen reduction reaction. And also we're looking at designing new interface materials for sulfur lithium all solid state electrolyte. There's something missing here. All solid state electrolyte batteries in collaboration with Professor Lee at Concordia University. You'll find that a lot of the research we do combines theoretical predictions with experimental measurements or even guidance from experimental collaborators and reciprocally. So we try to exploit really the synergy between experiment and theory and modeling and simulations at this point. And I want to have time to talk about really these approaches we try to develop towards environmental remediation, such as designing frameworks, whether they're metal organic or covalent organic frameworks for capture of toxic molecules, but also sensing applications for all sorts of pollutants. All right, so essentially today I'll talk about super hot semiconductor materials, and if I have a bit of time, I will also talk about our work on catalyst development, exploiting both our traditional or conventional DFT approach, but also accelerated by machine learning as much as we can. All right, so the first topic, maybe the main topic that I want to talk about is the electronic factors that we should take into account when we try to model and predict the electronic and mechanical properties of certain materials. And our case study here is really about silicon-containing materials. So this is work by a recent PhD graduate, Hong Hu, who just defended his thesis a couple of months ago, and is now a research officer at the Digital Technology Research Centers of NRC in Toronto. And silicon, I don't think I need to elaborate a lot on this, is a crucial element with wide range applications across science and engineering, and for electronics and healthcare industries. And we'll be particularly interested in spinel nitride, so silicon spinel nitride. So they have a stoichiometry, a 3 to 4 stoichiometric ratio. And these are very hard materials that are typically used in ball bearings, for example. We'll also be looking at silicon oxides, one of the well-known structure of which is quartz, and extensively investigated and documented experimentally, so it's a good reference point for us. And we will also look at silicon hydrides under high pressure, because these materials are believed to be good high-temperature superconductors. Okay, so by high temperature, we mean maybe room temperature superconductors. It's all in relative terms when we say high temperature here. Okay, so very briefly, we will use DFT in various implementations, so standard cone sham DFT with some, PBE or over exchange correlation functionals. Basis sets will use both numerical atomic orbitals or plane waves, depending on the situation. And we can go beyond conventional DFT if we want to do a good job on band gaps. And so we will be using these more elaborate methods, such as DFT minus 1/2 or the green function type methods, or even hybrid DFT to try to reproduce experimentally observed electronic band gaps. Again, sort of to anchor our theoretical modeling to experimental evidence. Okay. And so we'll be looking at silicon hydrides, oxides, nitrides, and all this work really started or was motivated by some findings about carbon nitride and the Zen blend carbon nitride structure, which was reported to have a very, very, very high bulk modulus and hardness, so very hard material. And so, indeed, if you calculate the bulk modulus of carbon nitride, it's very, very high. But this is true for essentially all of the group 14 other metal, so either titanium or zirconium. So all of the spinal group 14 and metal spinal nitrides really have very large bulk moduli. So this is what we can calculate from DFT calculations. And what our experimental collaborators in France at Université Paris Nord and École Polytechnique, Andreas Zer and Holger Wack, are able to measure is the nano hardness, so we call it H. And they could compare the nano hardness measured for all of these phases of different materials to the calculated bulk modulus, and they could find an empirical linear relationship between hardness and bulk modulus. And we could exploit this relationship or extrapolate this so that we could evaluate the nano hardness or predict the nano hardness of theoretically predicted phases of carbon nitrides. Okay, so these have not been observed experimentally on only the zinc blend 1. And so from extrapolation of the calculated bulk moduli for those theoretically predicted structures, we find a nano hardness in this range here, about 90 to 70 gigapascal. And this was sort of a negative result in a way, because the goal in all this work was to try to find dense phases of carbon nitride that would be even harder than diamond, because that was the initial goal. And for a long time, physicists and engineers tried to look at different dense phases of carbon nitride and other materials, hoping to find harder materials than diamond. But unfortunately, fortunately for experimentalists, we can tell them, well, look no further. This probably, for these phases, it probably won't be as hard as you would like them to be. A very interesting feature that we noted for these materials is you can see that the elastic anisotropy of carbon nitride is much higher than that of all of the other metal or group 14 nitride by a factor of 4 or so. But it's also much higher than what it is for a pure metal, which is fairly anisotropic. And so we really wondered why carbon nitride has such a high elastic anisotropy compared to the other group 14 analogs, especially because those have the same space group symmetry. So you can expect different mechanical behavior if you have different phases, but within the same space group symmetry, how come we have such a different mechanical property? And so this has to be due somehow to electronic factors, because we have the same group, space group symmetry, different mechanical properties that must stem from electronic properties. And of course, as chemists, we should have known this all along. What's the big major difference between carbon and silicon and the group 14, other group 14 elements is that the d orbitals of silicon are actually much more accessible than those of carbon. If you look at the energy levels of the atomic orbitals. And so when you look at the densities of states for a material like carbon nitride, and here we projected them as a SPD contribution, of course you see that for carbon nitride, there is absolutely no contribution of the orbitals in there. They're way too high in energy to be accessible, even upon favorable interaction with bonding nitrogens. However, for silicon nitride, the silicon d states, which are normally unoccupied in most situations, acquire significant population, as you can see here in green. These are the d orbitals, or the d states. So bonding in silicon involves the 3d orbitals. Completely different from the gas phase picture, of course, where these 3d states are not available for silicon, right? So it's a purely condensed phase occurrence. And so the fact that we have a population of 3d orbitals, which have a more spherical distribution around the atoms, so favors the more isotropic electron distribution in the material and much less directional bonding than what you could expect from the overlap of p orbitals. And so this could explain, and if you look at the density here, you see that the electron density around the silicon atoms, and the same holds for nitrogen actually, are more or less spherical, which might explain the anisotropic differences. Okay, so we believe that's where this may come from. Now, if we look at the electronic structures of those silicon nitrides, so we can generate the band structure, and again, this is the density of states that I showed earlier. Obviously, those systems are semiconductors, so the band gap is like 3 eVs or so, but the band gap is severely underestimated by our conventional, so PBE DFT calculation. This is nothing new. This is a well-known problem due to the self-interaction correction that is missing in conventional CONCHAM DFT. And we can fix this by using more elaborate methods here. And it turns out that when we take into account so this more elaborate treatment of the electronic structure, we end up with band gaps that are in excellent agreement, or excellent to very good agreement with known experimental data. All right. So all that to show that we know how to handle situation for these materials and reproduce experimental observables with some confidence, right? Which again brings a level of confidence into our own calculations and predictions. We also looked at silicon oxides because the interesting thing, quartz has been investigated extensively. So looking at the density of states for the silicon oxides, we found that very similarly to the silicon nitride, the 3D states acquire electron population. You can see this from the d orbital population here in the valence region. And what is nice about quartz, at least in the context of our work, is that there is what I call orbital resolved X-ray emission spectra available that show that indeed the 3D band of the silicon is involved or can be observed in the structure of quartz silicon oxide. So this is so basically our finding of the involvement of the 3D states in condensed phase matter is actually in agreement with what is observed for silicon oxide. Again, we can work harder to get the electronic properties for silicon oxides that actually come close or agree with experimental data. If you look at the band gap for quartz silicon oxide, that's where it is experimentally. And if we use conventional DFT, we severely underestimate the band gap, but working harder with those Green's function method, or hybrid DFT, which comes as a lower cost than those Green's function methods, but still a much higher cost than conventional DFT, we're able to find band gaps within 1 electron volt. Okay, so we know the limitations of our calculations that way. So now we decided to look at silicon hydrides under high pressure conditions, because they are thought to be leading perhaps to a new generation of moderate temperature superconductors. So if you look at the gas phase silane molecule, so again you see that of course there is very, very little or no involvement of d orbitals in the bonding orbitals of silane. But when we look at the crystalline phase of silane, so we pack up those silane molecules together under high pressure. And if we look at, so this is sort of the crystal structure we get. And if we look at the density of states, we see that again, for this material, under some pressure conditions, we have a significant contribution of the D states to the bonding topology of the material. Okay, and this feature, okay, so this it's not necessarily obvious from that slide, but as you increase the pressure, we really find an increasing contribution. Maybe here you see a higher contribution of the d orbitals, and here an even higher contribution of the d orbitals to the bonding topology as you increase the pressure. Up to a point where at high pressure, and this is sort of the molecular structure or crystal structures that we get, at very high pressure, the band gap actually closes or vanishes. So where the 0 here is the Fermi level, and the system becomes metallic. All right, so we have to reach pressure of 250 gigapascal, and you see that now we're closing the band gap here of the orbitals. So this motivates investigations of materials under high pressure conditions to also try to stabilize materials phases that may not be observable under normal conditions. All right. So just to conclude on that part, so we saw that the silicon 3D states are very important in the bonding topology and the valence region of silicon-based semiconductors, whether it's nitride, oxides, and hydrides under high pressure. We can reproduce, or DFT calculations reproduce structural properties. I didn't discuss that, but they do reproduce known experimental structural properties very well, but also even the electronic properties such as the calculated band gaps. We just need to use the proper model, okay, to do that. And so the 3D states certainly play an important role in condensed phase silicon chemistry. And so, and again, by subjecting those materials to high pressure, we're able to access new properties such that that high pressure crystalline silicon hydride becomes metallic, possibly superconducting materials. All right, how am I doing with time?
We still have about 5 to 10 minutes.
5 to 10 minutes, thank you. So the next topics that I will just touch upon is something we started not too long ago. So it's in collaboration. So Mehdi, who is doing the work here, is here in the audience, so he'll keep me honest, or he will answer the tough questions that you may have on this project. But this is in collaboration with Arash and Danielle Gay here at UNRS. And so we started not too long ago to look at how we could combine our computational expertise and the experimental know-how and expertise of the UNRS team to design new catalysts for the nitrogen reduction reaction, so the NRR. And our main strategy at this point is alloying to find new catalysts. Okay. So basically, why are we trying to find catalysts for the NRR? We're trying to circumvent by electrochemistry, by an electrochemical process. We're trying to circumvent or bypass the industrial process for ammonia formation from nitrogen, which is the Haber-Bosch process, which is not an environmentally friendly process, and yet it's used a lot to generate ammonia in abundance, so that we can use them as fertilizers in agriculture. So finding electrochemical pathways to ammonia production from nitrogen, from the abundant nitrogen in the atmosphere into a high-value chemical like ammonia is a very important route towards, let's say, sustainable or green agriculture. Green agriculture, that's an interesting term. All right, so the NRR is known to proceed through different types of mechanisms. So the dissociative ones, where the nitrogen molecule is first dissociated, that's extremely costly, because the triple bond of nitrogen is very hard, is very strong, sorry, so it's very hard to dissociate. But there are associative mechanisms, so either the distal pathway or the alternative pathway, where we go through a sequence of steps. The protonation sequence is just different for those two mechanisms. And there is another, I should mention, in all fairness, that there is another mechanism, which is the enzymatic pathway. And this is an illustration at how Mother Nature seems to have designed better catalysts than any of the synthetic catalysts we can come up with, because enzymes can fixate nitrogen as molecular nitrogen, and then catalyze the dissociation and the bond making, leading to ammonia in a concerted way, as opposed to an addition, a stepwise addition of nitrogen add atoms, for example. All right, so we looked at these different, so at this mechanism from DFT calculations. And so the idea is, what kind of catalysts should we consider? And we want supports, or catalytic supports, that are good at absorbing nitrogen, but also good at desorbing ammonia. So we need somehow a low binding energy of ammonia to the support and a high binding energy of nitrogen to the support. But something that I've not discussed yet, but the main competing reaction to the NRR with all the known catalysts around, one of the major issues is catalyst poisoning because of the hydrogen evolution reaction, the HER. So our strategy is to use catalysts that are poor, that have poor activity towards the hydrogen evolution reaction, and try to improve these catalysts materials by alloying, so sort of fine-tuning those to better accommodate sort of the nitrogen adsorption, all right, as our key step, or nitrogen add atom adsorption. And so along that line, we looked at so some of the P block and D block elements, and so definitely want to look at these metals, which are really poor catalysts for the hydrogen evolution reactions. And so we started with silver and tin, mostly based on the information available in the literature when we started that project. And so so this is a slide where basically that shows how we actually calculate the free energy profiles and account for the applied potential. So we looked at the typical intermediates. So we're going to use the computational hydrogen electrode, which is sort of a shortcut where anywhere we have the proton and the electron energy or free energy, we'll take this as the chemical potential for this entity as just the free energy of, or half the free energy of the hydrogen molecule. So we can evaluate the free energy of the intermediate by standard procedures, and we take into account the effect of the applied potential by just adding a term on top of our DFT calculation that up to this point ignores the effect of the electrode potential, which is something I'll get back to towards the end. So computational details, we use that exchange correlation functional with those projected augmented wave pseudopotential methods. So we use that type of slab here, 1x2 slab. Right. And so we use the quantum espresso program for these calculations. OK, so here is a free energy profile that we characterize for the NRR on so this type of alloy, silver tin, so silver-free tin. And so you can see that we have a high barrier for adsorption of the, let's say, the first intermediate step. So this is the N2H adduct. And so this is for the, so in black was the alternating pathway. The distal pathway involved essentially the same first step. If we look at the potential limiting step from the electrochemical point of view, this would be the highest free energy barrier encountered along that free energy profile. So for both pathways, in fact, on silver tin catalyst, the potential limiting step is 2.5, around minus 2.5 volts, which is only a minor improvement compared to pure silver. Okay, it's only 10% improvement, and this is really nothing comparable to the electrochemical potential used in actual catalysis of the NRR, such as on ruthenium catalyst. The potential of about 1 volt is sufficient to get the reaction to proceed. So really, we're trying to get under 1 volt over potential in our design of effective catalysts. So I will pass on a D-band model here because of for the sake of time. But where we're going from there is now to try to accelerate our design of catalysts by making use of machine learning, because we don't want to do DFT calculations of the entire free energy profiles for each type of alloy possible. I mean, this would be an immense task to do. And also, we have different structures for the alloys as well, so you can see the complexity of the problem increases exponentially. So we'll use machine learning to sort of predict the materials that we should put to the test from DFT calculations. And so we have a training set here of different alloy slabs with different materials. So this we can calculate. We calculate their electronic properties, such as the D-band, the D-band model, the D-band features of the active catalytic site. So these are used as our descriptors. We use machine learning in various implementations. The very first implementation was just artificial neural networks, but Mehdi can tell you that he's moved on now to more elaborate methods. But anyway, so the idea is here to predict, our target is to predict the absorption energies of nitrogen or the nitrogen add atom onto these supports, because there is an empirically observed linear relationship between the adsorption of nitrogen to the theoretical overpotential. All right, so we make use of this, and then we get heat maps of the theoretically predicted overpotential for different types of alloys, and now we know that maybe depending on the type of structures, okay, we have those different types of structures. So silver manganese or silver vanadium catalysts might be, or materials might be good potential catalysts. So we're not putting them to the test of DFT calculation of the free energy profiles and an experimental validation in Daniel's lab. And so basically, this is sort of an outlook slide for this. We want to go beyond the computational hydrogen electrode model because so far we haven't really accounted in our calculation for the actual role of the electrode potential. So this will be important, for example, even in determining the surface coverage of ammonia with respect to the hydrogen add atoms. Okay, so that will be dependent on the potential going through the material. So this is essentially where we're going. So with that, I'll thank the funding agencies that, so the silicon work, the silicon condensed phase work was funded by NSERC. The Electrocatalysis work was funded by an Audace grant from FRQS, which Daniel Gay was principal investigator. And we do all of our calculations on the Digital Research Alliance of Canada infrastructure, formerly known as Compute Canada, and so on the Calcul Quebec servers. So thank you for your attention.
Thank you very much. We have time for maybe a few quick questions.
Can you define what is nano hardness and how you calculate that?
How, sorry?
How you calculate it, the nano hardness.
Oh, we don't calculate the nano hardness. That's yeah, this is where we make use of experimental data. So on the horizontal axis, the shear modulus is what we can calculate. The shear modulus, the bulk modulus, that's straight from the crystal structure. The nano hardness is what is measured experimentally by our collaborators. So they found a linear correlation, more or less linear correlations here. So we use this to estimate the nano hardness from our calculated bulk modulus. Okay. So essentially, we told the experimentalist collaborators, if you manage to identify or stabilize those phases, this is a nano hardness you can expect to find.
Okay.
All right. So they knew that their experiments, their Anvil cell setup would be able to catch this because they can do diamond.
Okay.
So maybe they'll try to find those phases.
Yes. About the silane work where you showed that there was some D character in the valence band. A bit intrigued to see how that happens. Now, one thing is that does it depend on the distance between the hydrogen and the silicon atom? And could it be an effect of the projectors? of you know, because you're using a projector on the silicon atoms and that's seeing the oxygen orbitals. Something like that.
So you mean for for the silicon oxides?
Yes, your silicon oxide, like.
Silane or the oxide?
Huh?
The silane.
No, it's the hydrogen one, the silane.
Oh, the hydrogen one. Okay.
Yeah, that
so
one.
here's the band structure. Yeah.
That structure, yeah, sorry. Yeah, so I'm a bit intrigued that you find so much D character just by making the crystal. So if you do the crystal but without pressure,
That's essentially it, right?
you see
This
so
is
much
that
D
regular-
character in it.
Yeah, we already see. I mean, we think it's a condensed phase feature. Anytime you put silicon in a condensed phase, then the 3D orbitals, which are not that high in energy for silicon, become available.
But you mostly have SiH4 molecules, a molecular crystal.
Yeah.
And there's such a difference just by because they are van der Waals distances from each other, no?
At this, yes, at this pressure, yes, they are. No, they're already compressed. Sorry, they're already compressed.
Are they using the same code?
Yes.
Yes. Okay. Okay.
Yeah, all the same codes.
So for the ammonia, do you do you think that you can separate the hydrogen from water on the same surface as the nitrogen, or do you think you have another surface that you're putting nearby, and just bringing the hydrogen?
So I'm not sure I understand your question. So
I mean, the hydrogen you take it from water in what you're modeling. So
Correct.
are you splitting the hydrogen on the same surface and the same catalytic surface as the ammonia?
Yeah,
As the
yeah.
nitrogen?
Yeah. So that's why we have the competing. So the idea initially for the alloying was to try to mix an element that is known to be a good catalyst, let's say for nitrogen reactions, with one and both being bad for hydrogen adsorption. Okay. Because they do compete. I mean, we can look at the free energy profiles, and they will compete. So another approach. So rather than fully answering your question, I will tell you that another approach that we're looking into is to limit the availability of hydrogen, those protons. So actually, the ongoing research is to actually use non-polar solvents instead of water. All right. So or polar solvents that are not as good hydrogen donors, like ethanol, for example. So it's just to limit, to restrict the availability of the protons. And that's an issue when we're designing materials for all solid-state electrolyte batteries, for example. We don't have that issue of the water there. So we're trying to get some inspiration from that work as well, from the solid-state electrolyte batteries into designing or engineering new electrolytes, actually, that will so sort of circumvent the problem of the availability of protons and the competing HER process.
Great. With that, I'm sorry. Coolberry, you got to raise your hand in the beginning. Sorry. We have to move forward, so let's thank Professor Peslherbe one more time.